the title of my talk you see, and I want to recall some definitions. Riemann-Liouville fractional integral, Riemann-Liouville fractional derivative, and the Dzhbashan-Nersesyan fractional derivatives, which are associated with a set of numbers alpha k between 0 and 1, including 1. Professor Pshu describes such derivative, and we see that this derivative consists of several Riemann-Liouville derivatives of the order between 0 and 1, and one Riemann-Liouville integral. What?
One slide before, please.
Alpha k minus 1 less than 0.
So this 1 is subtracted from all alpha k, and in the next factor, 1 is subtracted from k.
Yeah, that's confusing.
Yes, alpha k minus 1 index and alpha k index k minus 1. And it is mentioned that these derivatives include as special cases Riemann-Liouville fractional derivatives, Gerasimov-Kaput fractional derivatives, and Hilfer fractional derivatives also. If we consider differential equation of first order in a Banach space, linear, homogeneous, we know that the resolving family of operators is a semigroup of operators. And resolving operator, it is a map from the initial state of the system into the state at the time t. For every t, it is operator, and for all t, it is family of operators. And if equation 1 has a resolving semigroup, then we can represent a solution of this equation. We know that the Cauchy problem for equation 1 will be uniformly well posed, and we can write solution of linear inhomogeneous equation, and by this formula using resolving operators. And for semilinear equation 3, we can reduce the Cauchy problem to this integral equation, and this integral equation can be used for search of solution of the Cauchy problem, for example, using fixed point theorem. And the same we have for equations with fractional derivative. Let it be Gerasimov-Kaput fractional derivative, and it will be usual Cauchy problem, but with m initial conditions, and the solution of the Cauchy problem will have this form where St is resolving operators. Now family of resolving operators hasn't semigroup property, but other very useful properties present in our case. And we can write a solution of the Cauchy problem for linear inhomogeneous equation. Here delta depends on the maybe it in the case of Gerasimov-Kaputto derivative it will be 1 minus alpha. And we can study quasi-linear equations. We reduce the Cauchy problem for quasi-linear equation where nonlinear operator depends on Young's derivatives. We can reduce this problem to this equation, integral differential equation, without the oldest fractional derivative, and we can study the issues of solvability for quasi-linear equations. Here several references, two monographs about semigroups of operators, work of Da Prata and Iannelli on resolving operators for linear integral differential equations in Banach spaces, monograph of Jan Pruss about resolving families of operators for integral equations in Banach spaces, and work of Emilia Bazhlekova, where she studied resolving families of operators for equation with the Gerasimov-Kaputto derivative. She obtained a generalization of Healy-Yasuda theorem on the generation of strongly continuous semigroups of operators on the case of Gerasimov-Kaputto fractional derivative, and other generalization was obtained for the case of analytic resolving families of operators. We will consider Cauchy problem, but maybe it can be called Dzhbashan-Nersesyan problem. But Dzhbashan and Nersesyan in their work call it Cauchy problem. 7 for equation 8, where here we have Dzhbashan-Nersesyan fractional derivative, oldest, and in initial conditions Young's Dzhbashan-Nersesyan fractional derivatives are used, and these derivatives associated with the same set of alpha k. And here operator A is linear enclosed, generally speaking unbounded. And here we have a definition of classical solution of problem 7-8. And our main aim is to obtain analog of Healy-Yasuda theorem for the case of equation 8. And we define the resolving family of operators for such equation. Here we require exponentially boundedness of this family of operators, linear bounded operators in a Banach space Z, and power singularity at 0 point, strongly continuous on positive semi-axis, and the equality of this strong limit to identical operator. Operators ST have to commute with operator A, and a function STZ0 is the solution of the Dzhbashan-Nersesyan initial value problem with arbitrary first initial data from the domain of the operator A and 0 other initial values. And we can note that if operator A is linear and bounded, the resolving family of operators for equation 8 has form of Mittag-Leffler function of this form. And for brevity, we will use such denotation. Sigma k is a sum of alpha k, alpha 0, alpha 1, and so on, alpha k minus 1. And we introduce into consideration a class of operators, linear closed operators. Operator A, linear and closed, is called the operator of the class, such class, for some constant, non-negative constant omega, if the following two conditions be satisfied. Неудобно тут. Я попробую так. Значит, if lambda from the right half plane in the complex plane, then a power of lambda belongs to the resolving set of operator A. There exists a constant k such that for all lambda from the right half plane and for all natural m, we have these inequalities. We see that if sigma n is a sum of all alpha k minus 1, if sigma n is equal to 1 and alpha 0 also is equal to 1, it will be Helia-Sida conditions. When sigma n is alpha and alpha 0 is 1, it will be Emilia-Bashletova conditions for which are necessary and sufficient for the existence of the resolving family for equation with Gerasimov-Kaputov derivative. Here we have such situation for our equation with Zhbashan-Nersesyan derivative. And this lemma is about the form of a solution of problem 7-8 when we have a resolving family of operators. This formula, where zk are arbitrary initial data from the domain of operator A. Some properties of resolving families, if there exists a resolving family for equation 8, then this family is continuous in the norm in the operator norm in the point t is equal to 0, if and only if operator A is bounded. This property is analogous to the property of semigroup of operators from the theory of semigroups. And another property, if sigma n is greater than 2 and A belongs to this class, then A also is a linear and bounded operator. Such property also known, for example, for Gerasimov-Kaputov derivative. And so if sigma n is greater than 2, then the situation is very simple. Operator is bounded and there is no questions. And we will consider also case of sigma n between 0 and 2, including 2. And here we will formulate our aim result, and it is known that such results, starting from the Helia-Sida theorem, can be proved easy into one direction. If there exists a resolving family, then operator A belongs to the required class. For example, here the same we have. If there exists a resolving family of operators for equation 8, then we can relatively easy obtain that operator A belongs to this class. But the inverse assertion it is very difficult to prove inverse assertion because we know that operator A from our class, we have the family of operators resolvent of operator A in the points sigma n, lambda in the power sigma n, multiplied by another power function. We know that if a resolving family exists, its Laplace transform will have this form, but we don't know does there exist inverse Laplace transform for this function, especially in an arbitrary Banach space without Radon-Nikodym property. And for representation of this resolving family, we use Phillips inversion formula, which passing to the limit, we will obtain from these operators our operators of resolving family. And we take such operators and we will consider, we will prove the existence of strong limit of these operators as m tends to infinity. And we will prove that this strong limit has all the properties of resolving family. So theorem has a form. There exists a resolving family of operators for equation 8 if and only if operator A belongs to the class. This theorem gives necessary and sufficient conditions for the existence of the resolving family, and in this sense generalize the Helia-Sida theorem. And we can discuss analytic resolving families. Analytic, when we, these families of operators can extend from the positive semi-axis onto a sector of the form sigma, a sector containing this positive semi-axis. And we introduce a class of operators, class A sigma n, for some theta 0, omega 0. It is a set of linear closed operators such that for every lambda from such sector in complex plane, lambda in the power sigma n belongs to resolving set of operator A, and for any theta between these two numbers and omega greater than omega 0, there exist constants such that this inequality is valid. And we can call such operators sectorial using similar to semigroup theory, when generators of analytic semigroups are called sectorial. And this technical denotation, and there exists an analytic resolving family of this type. It means that in the sector with the top in this point, with such angle and with such power singularity in the point 0, if and only if operator A belongs to the class A sigma n. And resolving operators has such form, Danforth-Schwarz type integrals, where contour gamma goes along the boundary of the sector S theta 0 on theta omega. This such result can be proved using such Savart type theorem. Here, this theorem is about the properties of the Laplace transform of the function which is analytic in a sector. And if we take delta is equal to 0, then it will be Savart theorem. And we can consider linear inhomogeneous equation with the same initial conditions. And using this denotation, we will obtain this theorem. If operator A from the class, it is operator A sectorial, F, here it is important, F from the class continuous in the graph norm of the operator A, or Hölder continuous in the usual norm. Then this function is a unique solution of problem 910. And this result also is analogous to the theory of semigroups of operators, and the conditions on F are the same, only in analytic case, in sectorial case. Одна? Хорошо. Perturbation theorem for the class of sectorial operators. For example, a sum of sectorial and the bounded operator will be again sectorial operator. And an example where we can consider all the cases. It is initial value problem for this equation in the space of sequences L2, but it can be considered as a sequence of initial value problems. And this here we can find easy spectrum of the operator A for various values of the parameter beta here. We will obtain that operator A beta belongs to the class C alpha 0, alpha 1, and so on, alpha n, belongs to the class A sigma n, either sectorial, or does not belong to these classes. And for example, such problem can be reduced to the previous problem, and we will obtain one of these cases. Thank you very much.
So, thank you very much for nice report.